Bom dia, pessoal, todos que estiverem assistindo a nossa transmissão de hoje. Então, hoje a gente está recebendo aqui o professor Ramses Snoeckx, from Abdullah University. Ele vai falar sobre combustão assistida a plasma, então todos fiquem à vontade para fazer perguntas e comentários pelo chat. No final a gente passa, podem fazer as perguntas em português, eu traduzo para ele depois. O professor, ele faz um trabalho excelente na parte de simulação de plasma, principalmente química de plasma. Então, esse seminário acho que vai ser bastante interessante. Ramses, I would like to thank you again by to accept this invitation. It's a pleasure to us to receive you here online. Okay. And, well, feel free to do your presentation, and thank you again.
Perfect. Yeah, I'd like to thank you as well for this opportunity. It's nice to see you again and being able to talk a bit about my past research. So, welcome to everybody who's watching. So today I will talk about plasma-assisted combustion, unraveling the chemistry. And I do this research in the King Abdullah University of Science and Technology under the supervision of Professor Min-Suk in the plasma-assisted combustion lab. So some background about myself. So I did my PhD in chemistry in Belgium at the University of Antwerp with Professor Annemie Bogaerts on plasma technology, a novel solution for CO2 conversion. And I mainly did chemical kinetics modeling and experiments for CO2 and reforming chemistry. So currently I'm a research scientist at KAUST with Professor Min-Suk, and I'm working on plasma-assisted combustion, again, chemical kinetics modeling and experiments, and mainly looking into the combustion chemistry. And if you have any questions, you can always contact me at my email address. So before I go into the backgrounds of my research, I'd like to give a brief overview of the history of fire. So fire has been very present in a lot of mythological tales and has been very important for our culture. So one of the most well-known is the story of Prometheus. And so I'm not talking about the movie, but about the Greek titan who stole fire from the gods to give it to humanity. So, and when Zeus found out, he was severely punished for it. But according to the mythology, it led to serious advancements in the human culture and society. So, of course, a lot of these mythological nature of fire is still present in our day-to-day lives, like the lighting of the Olympic flame still corresponds to the lighting of fires at the Greek temples. And today, it shouldn't come as a surprise why fire was such important in all cultures' mythology, because the control of fire by the first humans 1 million years ago contributed to hunting, cooking, heating. So it was very important for the first cognitive revolution. And next, it led to fire played an important role in several other evolutions, like the agricultural revolution, going from the Bronze Age to the Iron Age, where control of fire led to the development of different materials, which further improved several industries like agriculture and so on. So very quickly, fire became the cornerstone of civilizations, making everything in day-to-day life possible. So, and this is reflected in several iconic video games, as I just showed, like Age of Empires and Sid Meier's Civilization. So it's still very much present in today's culture. The next, fire caused the replacement of man-made power with fire through the invention of the steam engine, the invention of the combustion engine, and this fueled the Industrial Revolution. So today, everything in our day-to-day lives is connected to combustion to fire or combustion or petrochemical industry, which all rely on fire. So, but additionally, if we would look back at the mythology of the Greek titan Prometheus, in the end we know that a Pandora's box was opened, because not only Prometheus was punished, but also humans were punished for this acquisition of fire. So we could wonder whether the increase of pollution, the increase of CO2 in the atmosphere leading to global warming, maybe this is the opening of our Pandora's box. But luckily, we know that we shouldn't wait for the end, but rather look for new solutions. And maybe plasma can provide a solution to avert all these negative effects. And so one could wonder, like Prometheus and Zeus in this Greek mythology, the ultimate power of Zeus was lightning, which is electricity, and lightning, as a coincidence, or maybe not a coincidence, is plasma. So plasma, maybe it's predestined that plasma could play an important role in our lives and in solving the problems we're currently faced with. So let's start with what a plasma is. Plasma is actually the fourth state of matter. So when we add heat or energy to matter, we go from the solid state to the liquid state to the gas, and eventually to the fourth state of matter, plasma. Where a gas is neutral, in a plasma, the gas is ionized. So this is also why plasmas are called sometimes ionized gases as well. We could also represent this by the angry particle in states of matter. So if we look at plasma, the angry particle says that he's like lost in a chaotic sea of fools. And I'll show you a bit why maybe the angry particle has some, why there is some truth in his feeling lost in this chaotic sea. But I hope I will be able to help you in this presentation to see that there is some order in this chaos. So there's different ways of how to make a plasma. As I mentioned, it's through the application of more energy to the states of matter. So if we apply a lot of energy, like our own sun, for example, we can create plasma, because our own sun is a perfect example of a plasma. Other possibilities are applying a very high voltage. And another natural phenomena is lightning. Lightning is a very high voltage difference between the ground and the clouds, and as a result, you get a plasma. So besides heat and electricity through high voltage, you also have strong magnetic fields which can create plasmas, and one could consider the northern light or southern lights a third way of a natural plasma, and a different way of how you can generate these plasmas. So as a quick thought exercise, how many percent do you think of the universe is in the plasma state? So I'll give you a few seconds to think about that. So actually, 99% of the visible universe is in the plasma state, mainly attributed to all the stars. Sorry. So mainly attributed to all the stars and the interstellar matter. So usually a lot of people are saying they want to be part of the 1%. So I've got some good news for you. We are all part of the 1%. Or maybe this makes you sad because you would rather be part of the plasma, because this is actually a quite cool state of matter. In any case, if we look at energy transfers in plasma, the easiest way, as I mentioned, would be like lightning. You apply a high voltage difference across a gap, which leads to an electric field being generated. The electric field will contain there will always be some electrons present in the air. These will accelerate get a certain amount of energy or temperature. That's why we write TE from electron temperature. Both these ions and electrons can be physically and chemically active, and the electrons can collide with molecules. These collision processes can lead to dissociation. For example, with oxygen, you get the dissociation into oxygen radicals. You could lead to ionization. The hydrogen is turned into the positive hydrogen molecule, and the generation of an additional electron, which will sustain the plasma. You also have electronic excitation. An excellent example is argon. Argon can be excited to several different electronic states. If these states fall back, you get light emission, which is why all these natural phenomena have such bright colors. This light emission, in turn, can again lead to photoionization. Then you have vibrational excitation. So, for example, nitrogen can be excited to the first vibrational level or the second or so on. And this actually is also given a separate temperature like Tvip from the energy or the temperature of all the vibrational molecules. These vibrationally excited molecules are also chemically active. And through collisional relaxation, they can transfer their energy to rotations or translational energy, which is then lost as heat to surroundings. So we've got a lot of things going on. We've got the generation of ions and electrons, which, as mentioned, are physically and chemically active. We got light emission through electronic excitation, vibrationally excited species, which are chemically active, and then also a generation of heat through these relaxation processes. So coming back to these temperatures, so I'll mainly be talking about this gas discharges, so not the plasmas which are millions of degrees hot like the sun, but more the plasmas which are low temperature, plasmas, which can actually still be up to several 10,000 Kelvin, but not the million degrees. So on one side, you have the non-equilibrium plasma, as shown in the northern light, for example, where the electron temperature is much higher than the vibrational temperature and much higher than the ground state or just gas temperature. So where the electron temperature is in the order of 1,000 to 10,000 kelvins, the gas temperature is usually in the range of several hundred kelvins or room temperature, for example. On the other hand, you have a near equilibrium plasma like an arc, where the electron temperature, where all the different temperatures or energies are relatively similar or the same, and the gas temperature is, as mentioned, several 10,000 kelvins. And then you still have specific plasmas which are in between these two. So, but continuing on the non-equilibrium plasmas, so why would we use plasmas? So in classic processes, usually we rely on thermal heat, radiation, or corrosive chemicals to initiate or activate certain reactions. While in plasma processes, we can make use of the highly energetic electrons that are used. So the gas temperature can remain very low or even at room temperature, while the energy comes from the highly energetic electrons. These then lead, as shown, to charged particles, why it's called a partially ionized gas plasma, excited species, and radicals. So it's a complex, but in my opinion, very beautiful mess is how I would describe it. And I hope this already helps a bit to not make you feel like the angry particles, so don't feel lost. Plasma is actually a very multidisciplinary field. So you have physics, engineering, and chemistry. Physics has been one of the most dominant fields in plasma, followed by engineering, and chemistry has been less highlighted, to say. So the applications of non-thermal plasmas are plentiful. You have airflow control, material processing, currently plasma agriculture, gas conversion, fuel reforming, plasma medicine. So there's really a wide variety of new applications that are being investigated. But as mentioned, I will be mainly talking about plasma-assisted combustion. So let's first start with the regular combustion. So combustion chemistry is initiated by chain initiation and propagation reactions. So usually you have let's check. So usually you have a fuel. This fuel becomes oxidized or gets split into smaller molecules. So for example, if we follow the blue arrows, this is what happens at lower temperature. So you get oxidation of the fuel, get production of HO2, hydrogen peroxide, and hydroxyl radicals. At very low temperatures, it has to follow a very long pathway to get to these hydroxyl radicals. At higher temperatures, we can go from this hydrogen peroxide to hydroxyl radicals. We can already dissociate the fuel into smaller alkenes. And at very high temperatures, you have this third pathway going straight to CO2 and CO and hydroxyl radical formation. So, but as mentioned, most of these, as you can see here, most of these processes require temperatures which are above 550 Kelvin. So at lower temperatures, they are all very, very slow to initiate combustion processes. That's why you need a high temperature to ignite the fuel. So besides initiation and propagation reactions, you have branching reactions. So as mentioned, the fastest one is the generation of hydroxyl radicals from a hydrogen radical and oxygen, which is very fast if you are at a high enough temperature. But once you start going to lower temperatures, the splitting of hydrogen peroxide becomes slow, and this very long pathway, as mentioned, is even slower. So how can plasma have an effect on this entire mechanism, or how can it enhance it? So combustion is characterized by thermal, kinetic, and transport effects, and a plasma discharge can influence all three of these to enhance the combustion. So for the thermal effect, actually, plasma-assisted combustion is already widely applied, because in most cars we have a spark plug, and this spark plug has actually a small plasma being generated. What this does is increase the temperature a lot to initiate these temperature-sensitive reactions, and which causes then ignition of the entire mixture in your combustion chamber. Besides this temperature increase, the generation of ions, electrons, radicals, excited species, they can all contribute to the generation of heat, and as such enhance the combustion. Another way how we can enhance the combustion is through transport effects. So when we generate ions and electrons or fuel fragments, we also have something called ionic wind. So if we would have a regular flame and we would look at the flow pattern, we would just have this regular flame. But when we apply an electric field, not enough to generate a breakdown, but just a low electric field, the ions and electrons will start moving to opposite directions. And as a result, the ions will actually create some kind of wind. So it's called ionic wind, which makes the flame go to one side or the other, depending on how the electric field is positioned. But what I will talk about mostly is about the kinetic effect. So the plasma discharge generates these fuel fragments, ions, electrons, radicals, excited species, and all of this will play an important role in the kinetics of combustion. For example, the direct electron impact dissociation reaction, so methane and oxygen can immediately be dissociated into oxygen radicals or the methyl and hydrogen radical, already generating important radicals for the combustion process. Additionally, you have excitation reactions, which I'll show you soon how these can influence the combustion. And you have the ionization reactions. So normally, these radical reactions from the oxygen and hydrogen that are generated from the electron impact dissociation can lead to hydroxyl, can lead to oxygenated methyl species, and so on. The excited species can react with neutral species and also generate this HO2. And the ion reactions can generate different forms of ions, which are also important in combustion or in flames. So this is which reactions help with the initiation of the plasma-assisted chemistry. So if we would add an additional section to this diagram, plasma could result in the direct formation of hydroxyl radicals, could result in the direct formation of excited species, excited oxygenated species, and so on. Besides that, so that's how the plasma can contribute directly to the mechanism, but there's also new reaction pathways that accelerate chain reactions. So these reactions with the fuel and oxygen radicals that generate hydroxyl radicals are very fast. So you don't need to wait until the hydroxyl is generated here or until you have the free oxygen radicals, because the plasma generates them and then you get these hydroxyl radicals very fast. As mentioned, the excited species also play an important role. The reaction between a hydrogen radical and excited oxygen is about 100 times faster than the reaction with the non-excited species at 300 Kelvin. So this is also how new reaction pathways are present when using plasma compared to the combustion without plasma assisted. So to give you an idea of time scales and temperatures, I took these pictures from Professor Iguang Zhu. So you have the plasma chemistry, which is at, let's say, the nanosecond time scale, close to room temperature, which is this formation of these radicals, excited species, dissociation of the fuel. And then at 1500 to 2000 Kelvin and millisecond range, you have the traditional combustion kinetics. And in the intermediate range is actually where the both join and where you have the plasma-assisted combustion chemistry. So where the species generated by the plasma interact with the typical species from the combustion process. And so how does this play a role? Usually, if you have a flame, if we plot the temperature over the heat release and heat loss, if you have a very low temperature and a very low heat release to heat loss ratio, you won't have a flame, you just have the gas flow or the fuel. But if the temperature reaches a certain point and the heat release over heat loss ratio increases, you get ignition of your mixture, the temperature shoots up, and you have hopefully a stable flame or stable combustion process. Then if this ratio would decrease, again, the heat release and heat loss, at a certain point you would get extinction of the flame and you would be back at room temperature. So by generating these plasma reactive species, what you could do is get much better control over the entire process in the entire temperature range, rather than having this big jump from room temperature immediately to 1500, 2000 Kelvin and going back to extinction. So the plasma generated species can help with both a controlled ignition and extinction, for example. So we can, or at least I can understand why the angry particle is feeling like he's lost in a chaotic sea of fools. But let's see whether we can bring him, whether we can change his mind and see more of the order in it. So our goal was to make, our goal is to make a comprehensive C1, C3, oxygen, nitrogen, water mixture chemical kinetic set, so which we can use for plasma-assisted combustion and plasma-assisted reforming studies. Because actually, when we are, most of the combustion studies, for example, burn methane, creating water and CO2, and in reforming studies, we're interested in how we can use this CO2 and water to make new chemicals. So actually, it's the same chemistry, but just in opposite directions. So in the literature, there's a lot of information on low temperature plasma reforming studies at room temperature. Usually people use something like ZDPlasKin and plasma atmospheric chemistry. So ZDPlasKin is a certain model. And in combustion science, you have high temperature combustion studies above 1000 Kelvin. And usually people use ChemKin and one of the several combustion chemistries that are available. So what we are trying to do is combining both chemistry sets and models to be able to perform low temperature plasma-assisted combustion and higher temperature plasma-assisted reforming to get a better insight in what's going on in the chemistry part and the kinetics. So one of the crucial points is that a change in temperature changes the reduced electric field. So the reduced electric field is an important value in plasma. It basically gives you have a certain electric field, and the electric field is divided by the species density. So if the temperature goes up, as a logical consequence, the density decreases, and as a result, the reduced electric field changes. And a change in this reduced electric field has an important impact on the electron impact reactions. It changes rates of chemical reactions, which in turn changes heat release. And this change in heat release, again, changes the density of species, changing the electric field. And so we have a process that continuously interacts with itself. So we chose to make a model that couples ZDPlasKin and ChemKin on any time scale. We solve the electron and ion chemistry using ZDPlasKin, and we solve the neutral chemistry and the heat release using ChemKin. So first, let's take a look at diluted mixtures for a hydrogen-oxygen mixture. So what you see here is the experimental data from the group of Richard Yetter. So what they did is they took 2000 ppm hydrogen, 3000 ppm oxygen, and diluted it in 99.5% argon at 1 atmosphere. So the red crosses give the oxygen concentration as function of temperature, and the blue ones the hydrogen concentration as function of temperature. So this is the crosses are the experimental data, and the line where they're modeling results. So what you see is that with an increase in temperature, you have an increase in reduced electric field, and both oxygen and hydrogen start decreasing because the plasma starts to initiate conversion reactions. If we would plot the pure thermal case, you would see that there would be a straight line here, no conversion of hydrogen until about 860, and then suddenly we have this full conversion because the temperature is suddenly high enough to initiate combustion and thus full conversion. So this is how they use traditional flow reactor studies in combustion, and they applied it to a plasma system. Between the modeling and the experimental results, you see there's a small shift, like 50 to 100 Kelvin. And we tried using our own chemical kinetics model to see whether we could do any better with including the temperature calculation. So with the temperature calculation, I mean the heat release of the chemical reactions are also incorporated in the model. So if the combustion process generates heat about 30 Kelvin, then the reduced field is adjusted, and the chemical kinetics are adjusted in our model. So we used a typical thermal chemistry, extended it with ozone reactions, used a typical plasma chemistry with argon, oxygen, ozone, and hydrogen. And these were the results we got. So the full line are the modeling results, and we put an uncertainty interval by varying the amount of energy in the pulses with 30%. So next, what we did is we reduced our plasma chemistry. So we removed all the reactions, all the plasma chemical reactions with all the molecules except for argon. So we removed the dissociation of oxygen by electrons, dissociation of hydrogen, and mainly looked at the excitation of argon. Why did we do this? Because 99.5% argon is present. This metastable argon molecule is known to be very reactive, so it can be quenched with ground state argon, back to ground state argon, but it has much higher rates when being quenched with oxygen or hydrogen, leading to the dissociation. So this is why we removed all the plasma chemistry, and what we saw was that we got almost the same results as for our full model. So the mechanism in literature contained 39 species over 400 reactions, and our reduced mechanism was like 15 species and 82 reactions. So we have less species and reactions and much better agreement with experiments. So you would assume we are very happy, but actually we are not, because it tells us nothing about real-world situations due to this dominant effect of the diluting gas. So there's no real-world situation where you will have a mixture 99.5% diluted in argon. So as a result of this dominant reaction of the metastable species, which is then followed by thermal chemistry, we actually don't know whether any full chemistry set would be accurate if you would work in undiluted conditions, which will be all of your real-world applications. So the conclusions for this part is that depending on their concentration, metastable species have a dominant effect on the chemistry taking place, but mainly that there's no such thing as an inert gas in plasma studies. So these traditional combustion flow reactor studies, heavily diluting your mixture, are not a good approach to study this system. So next, we started to investigate undiluted mixtures. So we did our own experiments. We did 0 watt, which means there is no discharge present. So we get the same between 800 and 850. We get full conversion of the hydrogen present. Then we did 3 different powers, 5 watt, 10 watt, and 20 watt plasma power. And what we see is an increased conversion through electron impact reactions if we go from 5 watt to 10 watt to 20 watt. Another thing we see is in the range 675 Kelvin to 775 Kelvin, we see a decrease in the conversion or oxidation of hydrogen. In combustion, this is known as a negative temperature coefficient because the rates of certain chemical reactions decrease at higher temperatures, and as a result, the conversion or oxidation slows down or decreases. So we were wondering, maybe we have this negative NTC behavior, but we also looked further into some of the experimental data. So I already told you this reduced field strength is very important. So the electric field strength divided by the species density. So this is what we expected from the reduced field. So at 300 Kelvin, we have a certain reduced field. With increasing temperature, the density decreases, so the reduced field strength increases. And what we actually saw when we measured it is that in the same region between 675 Kelvin and 775 Kelvin, where we're thinking about this NTC behavior, we see a very big change in the reduced field strength. So probably the visible effect is also a physical effect, which is leading to this drastic change in the reduced field strength, and which influences, which has a significant influence on the electron impact reactions, and thus, as mentioned in the beginning, when developing the model, this will also influence the chemistry. And this is something we are planning to look into further. So the reactor we used here, important to mention, is a dielectric barrier discharge. So this contains a dielectric, and the dielectric is also influenced by the temperature. So possibly this is also contributing to this change in the discharge behavior and leading to several significant physical effects. So if we use this reduced field that we measured in the model, we're actually able to reproduce this NTC behavior. So the full line and the full dots are the experiments, and the open dots and the dashed line are the experimental data. So we see an increase at low temperatures. We reach a maximum, we get a decrease, and then an increase again. So this shows that the model, taking this reduced field into account, can actually account for this NTC regime. And what you probably also notice is that at lower temperatures, the model underestimates the oxidation or conversion, but this is the result of additional heat being generated in the discharge, which is not yet taken into account in the model. So at these low temperatures, the chemistry is very sensitive to the temperature. So on general, a DBD generates about 100 Kelvin additional heat. And if we would supply this additional heat, then we see that the conversions are actually much closer to the experimental values. So looking more into the product, so into the underlying chemistry of this behavior, because actually what we can see here is a slow increase in conversion, a very rapid increase, a decrease, and a second phase of a very rapid increase. So if we look at the products with FTIR, we see the production of ozone and, of course, water. And the ozone production decreases when we go from 300 to 900 Kelvin. And at 750 Kelvin, there's almost no ozone. So the ozone is formed by dissociation of the oxygen molecule into oxygen radicals and then recombination to ozone. Ozone is known to have a low reactivity at low temperature. That's why at 300 Kelvin, a lot of ozone is generated. The reactivity increases with temperature, which is also clear from our FTIR spectra. We have a decrease in ozone with increasing temperature. But this means that at low temperatures, there's actually competition for oxygen radicals. So you have the process where oxygen radicals recombine with oxygen to form ozone. And this is in competition with the reaction of oxygen radicals with hydrogen or hydrogen radicals to form the hydroxyl radicals, which are so important for the combustion or oxidation process. So this would explain why in the first part at low temperature, the conversion only increases slowly, and then starting from 600 to 750 Kelvin, there's a strong increase due to the liberation of these oxygen radicals from ozone. So from this part, there's a lot of further analysis still required, but so far we have seen that there might be an NTC regime present for hydrogen conversion. It could be a combination of the chemical and physical effects, so we need to investigate it further, also with other reactors where we can maintain a more stable reduced electric field. The chemistry is mainly driven by electron impact dissociation of oxygen. ozone plays a key role in the availability of oxygen radicals and the hydrogen conversion and oxidation, especially at these low temperatures. And its role changes heavily depending on the temperature. And there appear to be drastic physical changes to the discharge we used above 675 Kelvin. So what we are currently investigating is hydrogen, oxygen, nitrogen mixtures. So these are some of the first results. So the same reactor, you can see the blue lines are conditions where there is an abundance of oxygen, so which is called burning lean in combustion. So in these lean conditions, you don't see the presence of this decrease in the NTC regime, but starting from 1 and from rich conditions, you actually see that this behavior with this dip, with this NTC behavior, starts to appear again. So this shows that the presence of oxygen and probably ozone plays an important role, but that nitrogen has a strong influence on whether this role leads to this behavior or not. So when we look at the FTIR for these products, what we see is that for these lean conditions where there's an abundance of oxygen, we get the formation of N2O, NO, NO2. So here too, a lot of N2O, NO, NO2. And for these rich conditions, so where there's no abundance of oxygen, we don't see the formation of NOxes. This is actually also an important critical point for plasma-assisted combustion, because what a lot of people are trying to do is we want to work at lower temperatures, so you have more efficient combustion processes, so you're able to burn leaner, use less fuel. But what we see here is that if we have nitrogen present in these very lean conditions, you get the formation of NOxes, which are, of course, not a product you want from combustion, because these are very polluting chemicals, which can lead to smog and acidic rain and so on. But so we see for these fuel-rich conditions, we don't have these NOxes. So probably these NOxes play an important role in the behavior we noticed here with this decrease between 600 and 750 Kelvin. Sorry, I mean that the decrease is not present for the lean conditions where the NOxes are present. So, and we can explain this by the creation of an additional reaction pathway for HO2. So when we create NO, this can react with HO2 to form NO2 and hydroxyl radicals, which in turn leads to a catalytic cycle of the NO2 reacting with hydrogen radicals, going back to NO and generating more hydroxyl radicals. So this pathway results in something known as chain propagation instead of termination. And this is probably why there is no NTC behavior when the NOxes are present, because they generate much more hydroxyl radicals. So to conclude, I would also like to show you something about plasma-assisted reforming. So I showed the work on plasma-assisted combustion, how the chemistry plays an important role, how both the temperature, the physical effects of the reduced electric field are playing an important role. But as mentioned in the beginning, combustion and reforming, chemically speaking, they're just opposite reactions. So plasma-assisted reforming, the rationality is the global warming, as mentioned. We know CO2 concentrations are increasing and that this has a detrimental effect on our climate. But this is actually a window of opportunity because we have a lot of investments in renewable electricity, and plasma can use this renewable electricity. So if we would use something like the waste, or CO2, for example, together with hydrogen or methane or water, and convert it back to chemicals and fuels or a new feedstock, there's different ways. You have biomass, you have direct solar energy, you have this big solar thermochemical conversion plants or photochemical conversion. And then you have indirect renewable electricity. So most well known is the electrochemical conversion, water splitting into hydrogen, but actually plasma chemical conversion would have can have a very big impact in this area as well. So the basic idea is that you utilize the waste, CO2, for the production of solar fuels or new feedstocks. You can do it through pure CO2 splitting. You can convert it with a co-reactant, which is dry reforming of methane if you use methane, artificial photosynthesis when you use water, and hydrogenation if you use hydrogen. So the advantages of using a plasma for these processes is that they operate at room temperature. You have a large feed flexibility because you can use both CO2, methane, water, hydrogen, it doesn't matter. You have high operation flexibility because you can turn the plasma on and off when the electricity is available. You don't have high long heating times or cool down times. The process is not sensitive to that. You have low reactor cost, simple scalability, and you use no rare earth metals. But maybe most importantly, if we look at dry reforming of methane, so CO2 and methane, usually with thermal processes, this yields a mixture of CO and hydrogen, known as syngas. But with plasma, we're actually able to generate other products as well. We are able to generate higher hydrocarbons in one step, or even oxygenates in one step. So this is a big advantage over classic thermal processes. So the main challenges in this area is that plasma possesses important advantages over other CO2 conversion and reforming technologies. But a lot of research and challenges remain, mainly in the short run for pure CO2 splitting. It's been shown that this could be cost-effective, pure CO2 splitting, but of course then you only have CO. And in the long run, there's a very big potential for direct oxidation of CO2 and methane to fuels such as methanol or formic acid and so on. So to conclude this entire presentation, I would like to say as some take-home messages is that this worldwide shift to electrical and mainly renewable energy, but even if it's non-renewable, even if it's something like fusion or fission, this provides a great opportunity for plasma technology to complement, such as plasma-assisted combustion, or even entirely replace fire, such as in the reforming processes. And plasma technology can have a very big impact on incorporating this renewable electricity or renewable energy sources, both in the petrochemical and energy industry. And as such, plasma research could contribute a lot to prepare these industries for an electrified future. And of course, the future will be a combination of technologies: combustion, plasma, catalysis, electrolysis. It won't be a one-size-fits-all solution, but a combination. And we will go more to on-demand tailored chemistry rather than big bulk plants. So I would say that further insights in both the plasma chemistry and physics will be key to advance all of these applications of plasma technology and to unlock its full potential of plasma technology. So, and then I'd like to thank you again for inviting me and for your attention. And I'm ready to answer some questions or comments that you have.
Okay, thank you, Oden. So it's a very nice talk. I have questions. To the audience, feel free to ask questions. So, podem fazer as perguntas em português, eu traduzo, à vontade. I have some questions. First of all, you said that the heating by plasma, it's not taken into account yet. How do you plan to input these or not?
In a first step, the idea is just to measure the heat and implement it in the model to see whether the fit increases. But of course, then we only have the solution for one for the experiments we did, and not a generally acceptable solution. I know there is some work already done using ZDPlasKin to include heating, resistive heating, I believe, or electrical heating, and vibrational to translational relaxation. But currently, because currently I'm focusing on making a more simple chemistry model, so it's easier to adopt. So a lot of the vibrational reactions are currently not included, but that's also one of the steps when you have the vibrational species included and you have all the relaxation processes. Those could also help with the heat release.
I think your work and this type of work is extremely necessary. I am not chemistry, and work with combustion, there is a lot of questions about what is happening, and the model, a simple model, is very important to beginning. And when I made my PhD, there is a lot of works using diluted mixtures that it's not useful. So it's very important to see closer to the real world. And I have an important question. In your goal, you said that you want to build a model for C1 to 3 fuels. And I think there is a lot of difficulty to find reaction rates or cross sections for plasma reactions. Can you talk about it?
Yeah, I agree. Like for C1, a lot is available. For C2, enough is available, I think, to make a realistic model. But starting from C3, it becomes difficult. The data is not available, so you need to start to extrapolate. And then we're only talking about the electron impact reactions. Then we're not yet talking about the reactions of all the plasma species, all the radical reactions. Like even so, we started with hydrogen oxygen to build the base building block, and then we'll go to CH4 and then so on. But even already for hydrogen oxygen, so I've shown that ozone is very important. It's very difficult to find recent data of ozone with all of these neutral species. And most of these diluted models did not include this data because it appeared it was not necessary. But as mentioned, that's because it doesn't represent reality. So I had a hard time finding all these reactions, and I imagine the next step, methane, but especially higher hydrocarbons, that will be really challenging.
One experimental question, if I may. How did you measure the reduced electric field?
Sorry, how did I measure that?
The reduced electric field.
Okay. So because we had the DBD, we used Lissajous method And so at this temperature I mentioned, like 650, 675, you see that the Lissajous starts like shifting. It's still how's it called? Parallel? No, it still has the typical shape, but it starts getting compressed and moving. So the breakdown voltage starts. Now I have to see I say it correctly. I think decreasing, and the charge starts increasing.
Okay.
So this is some. So there's two things we plan on doing: either see whether we can identify this effect and looking at the reactor without dielectric to not have this effect, but then you start ending up with nanosecond discharges, and there it's almost impossible to measure the reduced field.
Yeah.
There you need to estimate it using a model usually. So it's there's a lot of room for investigating these effects.
Yeah, I have a doubt. You said that you use the plasmachemical and the combustion chemistry together at any time scale. I have some doubt about this. Can you explain more?
So what the model actually does is it calls the ZDPlasKin part, so it calculates the rates for the electron impact reaction, all the reactions that are given for ZDPlasKin, and then it updates the densities and uses these densities as input for the ChemKin module, and calculates the reaction rates and the new densities in the ChemKin module, and then uses this as input for the ZDPlasKin. But so both models. So if I would say I'm modeling from 0 to 1 second, then okay, it's more like from 0 to 1 picosecond. Yeah. So from 0 to 1 picosecond, first it calculates the ZDPlasKin module, and then for the same time step the chemistry model, and then it goes to 1 picosecond to 2 picoseconds.
Okay. Yeah, I understand.
It's the, I think, closest to reality. It's still an assumption, of course, but due to the small time steps, I believe it's relatively accurate.
Okay.
Maybe you have another opinion, or
no, about this, no. Because this is a problem, man. I worked with linear discharge. Yeah. That's no steady state discharge, so we have evolution. The plasma conditions are changing. So the question about time scale is very important. But I do not have an opinion about this. I really. NO, it's a problem in plasma combustion. And in my experience, experimental, there is nitrogen, oxygen, and plasma. There will be NO. So normal. So of course, in the combustion, it can be consumed or not. So, I know. Your results of no NO at in field mixture, it's hydrogen oxygen mixture. I have a feeling that using hydrocarbons, maybe the NO will remain, but it's based on my experience. I am wondering about the NOx behavior when you use the hydrocarbons. Because it's a problem. My work and my colleagues' work, it's about reduce pollutant emissions.
Yeah.
It works well for CO, for unburned hydrocarbons, but not is always a problem because it increases using plasma. So yeah, only wondering about.
I think we will see that, because I think even in the diluted studies, it's or in flame speed studies, they see that things improve except for NOx. But so then it would be interesting if we get the model to work, to see, is there any way we can influence this? Can we try to find a different pathway, or maybe add, an additive is probably not going to work, but is there a way that we can have the positive effects and minimize this this addition of NOx? Yeah, I agree.
Okay. Our audience has no questions, apparently. It's normal. Then I think your work is very interesting. It's very important to the field to do. It's a very difficult work. It's need to make it in steps, as you know better than me. But it's very important to understand, to give some basis to discuss plasma system combustion. So thank you again by the very nice talk. I will read the paper after. And thank you again. Feel free to make any comments that you want to do. And
I don't have any specific comments. It was my pleasure giving this presentation for you, and I hope I was able to give some new insights, or at least show the progress in the plasma chemistry side, and how close actually it's still all linked, the physics, the chemistry, and then the engineering. So it's really the ideal field for interdisciplinary and multidisciplinary research. That's also what I like so much about it. So I hope that can also stimulate all the viewers and students present.
Okay, so thank you all that watched. So bye. So, yeah.